So 5.5 deals with z-scores, and we're just going to touch on that. A z-score refers to the number of standard deviations you are away from average. Okay, so remember the normal distribution graph. It looks like this. And so you can see, for example, if your score was right here, your z-score would be 1.3, maybe 1.3 away from the average, 1.3 standard deviations away. Remember the distance here to here is 1 standard deviation, standard deviation, standard deviation, right? Okay, also let's say you had a score that was, I don't know, maybe here. Can't really see that purple. But then your z-score would be 1 standard deviation, 2 standard deviations, maybe 2.2. And because it's on this side of the average, our z-score would be minus 2.2. So your z-score refers to the number of standard deviations away from the mean. Okay. So here's the information we're going to look at, and we're just going to read this through. Remember, this is very similar to the key ideas, which is in your textbook. You can look at that on page 263. A little bit different in there, but same ideas. Standard normal distribution. So we've talked about normal distribution. When we add the word standard, this is what it means. It means the average will be 0. Okay, and the standard deviation is 1. So we can think, if we were going back to here, if we're looking at a standard normal, then this line would be at 0. Okay, this would be 0, and then the standard deviation would be 1. So this would be 1 here, this would be 2, this would be 3, and when we go the other way, let me erase the purple here, then this line would be at -1, this would be -2 because it's 2 standard deviations away, and this is -3 because it's 3 standard deviations away. So when we talk about z-score, we're referring to this standard normal distribution table. So z-score is really easy here. If I have a grade right here, that would be about 2.4 for my z-score. If I had a grade way down here at the very 0.1% of all the data, my z-score would be -3.3. Okay? All right, so let's keep reading. A z-score is standardized value that indicates the number of standard deviations. We already talked about that. Here's how we calculate it. So your z-score, represented by z there, is equal to your data value, subtract the mean, so you're finding now the difference between what you got and the average, and then you divide by the standard deviation of the data, and that gives you your z-score, which is what we've talked about. Z-scores are good because if we look here and I said, let's give myself a good mark, I said I have a standard or a z-score of 2. And someone else, let's just say, for example, Mr. Thomas has a z-score of -1. We know that my score was 2 standard deviations above average, and Mr. Thomas's score was 1 standard deviation below average. So it's really easy to compare data when we talk about z-scores because it's all between -3 and +3 kind of thing. Okay. Back here, z-scores can be used to compare data. We talked about that. A positive z-score indicates a data point above the mean, yes, and a negative z-score indicates below the mean. Let's do 1 or 2 examples together. The math test scores in Ramon's class are normally distributed. Okay, so we know 100%, 1 standard deviation away from the average, there's going to be 34% of the data on either side, etc. The mean is 80 and the standard deviation is 5. Okay, let's stop this and sketch a graph quickly. All right, that's good. So you can see here the mean or the average is right in the middle. And then I added the standard deviation to get the intervals. And because it says it's normally distributed, we know that it'll kind of look like the bell curve, and that if I was to draw these sections, in this section there's 34% of the data. We know that it's their normal distribution, and we could do there too. Okay? All right, now she scored an 83, so we're looking about there on the test. Compare her score with the rest of the class scores. Okay, so if she's right there, we're looking at a Z-score. Remember, Z-score measures from the average or the mean, and each standard deviation is 1. So this Z-score, if I were to make an estimate, I would say the Z-score here would be, I don't know, 0.8. Okay, just under the 1. Let's use the formula. So the Z-score is calculated by your piece of data, subtract the average, divided by the standard deviation. So we're looking at 3 divided by 5, and if you do that division, so she has a Z-score of 0.6. Okay, so we can see that she scored higher than a lot of her classmates. If we consider that on this side of the average is exactly 50%, we know for sure that she scored higher than at least 50%. And let me fill in here up until her score. So this whole section is 34, so I don't know, I would guess that she scored 50 plus maybe another 20, maybe about 70% of other people were below her score. There is a Z-score table that we use to figure this out. Now, here we go. Let's have a look at it. I'm going to erase this writing that's on here right now. We use the Z-score table then to figure out the percentage underneath that Z-score. So we know that she had a Z-score of 0.6. You can see that along the left here is the tenths spot, right? So 6 or 0.6 we're looking at. And then you can see along the top is the hundredth spot. So we can actually look to 2 decimal places with a Z-score. So in actuality, what did we have? 0.06. Where's my purple pen? 0.60. So if we go to the hundredth spot. So if we look at the chart, 0.60 is here. 0.7257 of the data was underneath her score. If we turn that to percent, of course, we can say that 72.57% scored less than she did. And so that's the percentage, 57% is this blue area. And we can use or figure that out using the Z-score table. Of course, if we know that percentage, we can also figure out the percent of people that scored higher than her, this yellow portion, right? Underneath the curve we know is 100%. So if we want to figure out the yellow portion, the percentage of people that scored higher than she did, we would just subtract the blue, and we would get 27.43% scored higher than Ramon. One last example. So the average or the mean lifespan of a non-stick frying pan is 2 years, with a standard deviation of 0.5 years. So when we think of companies when they make these non-stick frying pans, I think that they have analysts to think of these things and do these calculations. They don't want a pan that lasts for 15 years. There would never be, their production would be low. People are not buying new pans every 2 years or 3 years or whatever. So this is something that people do calculate. The average lifespan of a non-stick frying pan is 2 years, standard deviation of 0.5. Again, we can pause here, and I'm going to pause, and I'm going to sketch that out. You can picture it or sketch it out on your whiteboard too. Okay, average goes in the middle, and then 0.5 years is the standard deviation, so we know the next 0.25, 3, and 3.5. And if we go the other way, we've got 1.5, and 1, and 0.5. Oops, there we go. All right, Carney is an avid cook. She wants to replace her frying pan after 65% of its natural life. When should she replace the frying pan? Okay, so 65%, if we think about this, we know that this half, of course, is 50%, right? So, and then one more standard deviation, if I would draw that in right here, of course, that would be 50 plus 34, which would be about 84. So we're looking, I don't know, about 65, about right there. But we want to find exactly. When we think about Z-scores, the Z-score at this point, the end of the yellow, would maybe be, I don't know, if we think of a 1 would be at 2.5, that would maybe be 0.3. Sorry, you can't see that. 0.3, maybe. Okay, so let us get our Z-score formula out and plug in the numbers and see if we can figure out the exact Z-score there. That would yield 65% of the data. All right, so we already know certain parts. We know that the mean is 2 years. Standard deviation was 0.5 years. The X, that's what we're looking for. We want to know exactly the value here on this x-axis. We want to know the amount of time that's going to yield the 65%. So this is what we're looking for. Now, 65%. Let's go back to our Z-score table. 65%, we know if we switch that to decimals, that's 0.65. So we go to 0.6 here, and we trace along till the hundredths is 0.5. You can see straight up here. That would be 0.65. And our percentage here, or our Z-score, I mean, is 0.7422. 0.7422 is the Z-score. Okay, let's stick that into the formula now and solve for x. Just as a tiny aside, I was a little bit off on my estimation. I see that 0.74 is 65%, so really, man, I should have been about here. If this, the Z-score would be 1 right here, then 0.7 would be just below it. So I can really even just erase this 0.3, and we could put a arrow where we're actually working at, which is right here, at a Z-score of 0.7422. That looks better. Okay, so let's solve it over here. We're going to multiply both sides by 0.5 and then add 2 to both sides to get an x of 2.3711. So we can remember that our units here are years. So when we talk about 2.3711, we're talking about 2.4 years she should replace her frying pan. Does this answer make sense? Well, yes. We know that exactly 50% of the wear happens at 2 years. And so at 2.4 years, she wants to replace it at 65% of the wear. Yeah, 2.4 years does make sense. How many months is 0.4? Just under half, maybe 5 months, 2 years and 5 months. Okay, there we go. We could tell Carney what to do now. All right, one more thing before we go here. A Z-score table is found in your textbook on page 592 and 93. There's also a Z-score table in Google Classroom for you to open and look there. All right. Okay, you can proceed on to the next thing.